Oh yeah, I saw that.
I don't know, just last time Samir asked me to record it, but I think if nobody need it, I think you don't need to record it. I don't know.
I guess
yes, you can. Yeah, you can record it.
GIN.
Yes.
Is Daddy still around?
No, he already come back in last year.
Okay.
Yeah.
So can you guys see the slides?
Yes, we can.
Okay, great. Okay, hi everyone. Oh wait, how can I check if anyone's still in the waiting room? Oh yeah.
I think if someone will in the waiting room, they will show up.
What? Do I still have problem with sharing?
No.
Oh, okay. Okay, yeah. So hi everyone. So thank you for coming to today's TOT talk. I'm going to talk about how to use HypoDD relocation program. So HypoDD is a well-developed program, and all its algorithm and the instructions are well documented. So it's quite an efficient program, and it has been used by researchers for many years, like because it's created in 2000 or 2001. So researchers have been using it for 20 years. Okay, so I guess most of you have taken Chuck's inversion method class, and you may have already learned about what is double difference, right? So I will get a quick review on the double difference method. And so this method is based on the Ree theory, so that the travel time for event, like for one event here to the station, it can be expressed as an integral of the wave slowness along its path. And if we linearize the equation, we will get a residual of the travel time. Like the residual, it means the difference between the calculated travel time with the observed travel time. And this residual is linearly related to the location of this event. So at this point, we have one difference, like the time residual, right? The calculated time, calculated arrival time minus the observed travel time. And we will introduce the second difference. Okay, so the second difference, there is an assumption here, like if two event I and event J, if they are close enough and they are both far from the station K here, their paths can be treated as the same. So the only difference between these two events' arrival times is caused by the distance between these two events. So here we have the second difference, and now we have double difference. So the double difference is just the difference between two events' time residuals. Like it's just yeah. So if anyone didn't get me, please ask questions now.
Okay. I'm getting you, Yixin.
Oh, okay, great. Thank you.
Thank you.
Okay, so let's see. And also because the time residual is linearly related to the hypocenters, and now the double difference is also linearly related to these two events, right? I mean the parameters of these two events. The parameters means the location of these two events. Okay, so after arrange this equation, and we can have inversion expression like GM equals D. So D is the time difference. Sorry, the residual. Like the calculated arrival time, the difference between calculated arrival time and the observed arrival time. And M is the M is the M is the hypercenter parameters like the model we need to get. And W is just the weight for each equation. So like it could help the program to better fit our model or our data. Okay, so let's talk about how HypoDD works. So this program first find paired events like event I and event J. Those are paired events, and calculate their arrival time difference. So a paired events, they mean, like I talked before, these two events should satisfy the assumption that they are closely located with each other and far from their station. And the second step is to apply the inversion method on our data model and to get the parameters of the hypercenters. Okay, let me see. Oh yeah, and for the first step, we can use two kinds of data. One is the catalog data, which is the kind of data you can download it from Iris. And the other one is the waveform correlated data, which is we do cross correlation for paired events and then get their arrival time difference. So obviously this second data is more accurate because it's doing the cross correlation and the arrival time would be more accurate. And for the second step, we have two approaches. One is the LSQR, the conjugate gradients method. This is an approach that's more appropriate for a large area with large amount of events. And the second approach is the single value decomposition method. It's more efficient for small system, and it can give much more accurate results. Like take my research as an example. I studied the New seismic zone area, and this area has over 4,000 events. And I can use the LSQR approach to do the inversion for the whole area at once. But if I use the single value decomposition approach, I can only do like 50 events each time. But the residual time can be lowered very much, like from 50 milliseconds to 10 milliseconds. And also the best thing is the SVD method can return errors, like the location errors, but LSQR doesn't. LSQR only give the time residual. Okay. So after learning about the algorithm of the program, we finally get down to how to use HypoDD program. So this is a program written by Dr. Felix Waldhauser, and I've attached the two links about his paper on the email, the reminder email. So if you want to check out, you can check that. First, we need to know HypoDD is a Fortune 77 program. So it's kind of old. So in order to use that, you need to make sure you have G for Fortune installed. And also to get this program, you can just Google it and get it from the USGS website. And it's well developed. It's a very well developed program, and it has instructions everywhere. Like you can see, here is my HypoDD folder. Is it big enough? Like you guys can see that? Do I need to?
We can hear you.
Oh, okay.
Yeah.
Okay. So this is the folder, the HypoDD folder. Like after you download from website, you can have this HypoDD folder, and when you open it, you will see the README file here. And all its code is in this source folder, the SRC folder. And when you open this folder, you can also see there are make file and README file, and yeah, this one we will talk later. And when you open the README file, you will see how to install, how to make, yeah, just how to install this program. You just tap make. It's really simple. So I need to see here. Yeah, so after you tap make, and this program will be installed perfectly, and it will be functioning very well. So let's see some examples. And yeah, when you open the HypoDD folder here, you can see examples, and when you open it, you will have like 2 examples. Like it said that the example 1 is for like a regular situation, and the example 2 is for some very I don't know, like more complex situation, like it can calculate a larger amount of events or data or something like that. So we will only check the example 1. So after open the example 1, and we see there are still, yeah, README file. So it's really well developed and well instructed. Okay, so when you open the README file, you will see there are 3 steps. The first one is to convert the catalog data into the DD format that the HypoDD can use later. And the second step is here, like you need to run the PH2DT. It's used to calculate the time differences for paired events, like event I and J, as I said before. And the third step is running the inversion for data we get from the second step. Okay. Okay. So before we do that, we need to prepare some input files. Like the first one is the catalog data, like something you can get from arrays, like this. Like in the folder of each event, you will have the catalog data, like the extension will be .arc like this. And a station file, like it contains the information of the station you need to use later. The format is like this. It's just the name of stations, latitude, longitude. Okay, so these are 2 files we need to prepare before we run HypoDD. So the first step of HypoDD is to convert catalog files into the DD format files. So the catalog data is just like this. The first line is the information for each event, and the following lines are here are the station names and all the information they need to use in HypoDD. And after converting that, you will have this, let's call it face file, because the extension is like this. So you will find, you will get the face file. So the first one is the first line here, also tells the information about each event. And the first number is the ID it will generate for each event. And also here, following lines are just the station name, like arrival times, and this is the quality of the arrival times. And here is the phase of this wave P or S. So yeah, you guys have questions? No. Okay. So after that, we will use the PH2DT. Yeah, so it's just our second step of HypoDD, like to calculate the time difference between each paired events. I want to show you some examples. So we will open terminal and you will see. I have some examples. Here I prepared some examples. So here is my input file. It says .face, but I think it's just the catalog data. And here we have the station file like this. And with these two files, we can use the PH2DT to do our second step to calculate the time differences. So the next step is we need to find where our HypoDD is so that we can use that to do HypoDD. Then this is the HypoDD. Just here. And SRC. Oh, that's another HypoDD. SRC and sorry. Oh, okay. Yeah. Sorry. Repeat. You. Yeah, here. You will use the directory of the HypoDD that you installed here, and you will get the source folder, and you just use PH2DT. There is a PH2DT folder here, and the PH2DT executive file, and you can just put the PH2DT in the input file here. Oh, sorry, I didn't show you guys what is the PH2DT input file looks like. Let's see. Yeah, it's like this. And yeah. So this is the PH2DT input file. It has the, you need to make sure you have the station information file and the phase file here. And also here you can change the parameters here. All those parameters are explained very well in Dr. Waldhaus's paper. And I can explain some, to take some example here, like this one is the distance between these two paired events to the station, so you can set the distance here, and also like how far you think is good enough for your two paired events. So here it set it as 10 kilometers, and also you can decide how many events you want to pair for each event. And so this is just the PH2DT input file. I have my phase file here, and my station file here, and I set all the parameters from here, so I can run it So it will give me the calculated time difference. And this is the calculated time difference result. Let's open it. Yeah, it's like this. So here, oh, it's too small. So here is the ID of each paired event. And here are the stations. And here are the time difference. And this one is the quality of the time, quality of the travel time. And here are the faces. Let's go back to the slides. Okay. So after that, we will have the yeah, as you see, we have the dt.ct file. That is the calculated time difference for the catalog data. And as I talked before, you can also have the cross correlation data. And I recommend you to use the Dr. Stephen Horton's cross correlation program. It's like this, you can ask him to get this program. Is really efficient, and the result can be used directly into the HypoDD program. And here is an example of the program, the cross-correlation program. So we have the cross-correlation data, the cross-correlation time difference data here, like this. And then after we have the time difference, we can do the last step of the HypoDD. It's just the inversion method. Okay, so yeah, here is all the input file names you need to use. This is for the cross correlation data. You can change it to your own, and this is the catalog time difference data, and this is the name of the result you want to use. Like it will just return result in this file. And also you can change all the parameters you want to change in this HypoDD input file. And also those parameters are explained very well in his paper. Let's see, like here the add_dat parameter here is to give you, you can choose to use cross-correlation data or catalog data, or both cross-correlation or catalog data. And here IPHA is for phase, and you want to use P or only S or P and S. And also here, like if you want to change the approach you want to use from LSQR, or you want to use single value decomposition, you can also yeah, you can set the parameters here. Yeah, and this one is also very important. Like this is the weight you can set for each iteration, and yeah, so you can set up the iteration like whatever you want. Like maybe you want the first two iteration have one set of weights. You can tap your tool and change all the weights you want to change, and yeah, and so on. So no matter how many iterations you want to use, you can change here. And here is the 1D velocity model here you want to change. Okay. So, so we have already done the second step for calculating the time difference. And now we will do the third step, which is the last step about the inversion. let's check the HypoDD input file. So here is, so I'm gonna show you only for only the catalog data, how to use catalog data to do HypoDD. So here is the catalog data I have from the second step. And what else you need to change? Oh yeah, here is the result file name. I want to add it. In here, let's check. We want to use network sources, so we can have more events involved. And this one is just for single source. If you change it to one. And the solution we want to use is LSQR. Yeah, and these are the weights I change. So okay, I don't think we need to change anything. And here let's run HypoDD. It's quite the same as the PH2DT, the second step. So you just So you just go to, there is a file, there is a folder called HypoDD, and there is an executive file called HypoDD, and you just put HypoDD input file here. So it will run. It's really quick. So it will run like this, and then the result we can see. Oh, sorry, it gave me errors. Oh, yeah. Sorry about that. The station fell. I didn't check before. Station, do I have station? Yeah, I have station files here. There is the station file. I have it in the current folder. So I'll just put station.dat here. And save it. Here, let's run it again. Oh yeah, yeah. Here we will have our result. Let's see, what is that? Do you still remember the name I set for our results? It's HypoDD.relog, and let's open it. Oh. Okay, so here is the result we will get from the HypoDD program. And the first column is the ID of each event. And this is the latitude, longitude we get as our results. I don't quite, oh, and this is the depth. And these three, I think, is the latitude, longitude, the depth perturbations or something like that. And these three, yeah, I don't quite remember that, but it all shows in his paper. Let's see. Yeah, so I found this paper here. So all the input parameters and output parameters are all listed in his paper. So it's really a well-developed program. And all things are very nice. At the input files. Yeah, so here, the first one is the ID, and the next three are latitude, longitude, and the depth. And then, yeah, actually, the following 6 numbers are not really meaningful. And then it's the time when the event happens, and then it's the time residual you have from this program. And this one can tell you, like, this one is the time residual, and this one is also time residual, but this column is for the catalog data. So if you use only catalog data, you will have your time residual here, but this column for cross-correlation data will be -9. And if you only use cross-correlation data, this one will give you the time residual, and this column will be -9. So if you use both data, you will get numbers in these two columns as well. Okay. So I think this one is just the magnitude. And for numerical assessment, so the magnitude is really small. Okay. So I think it's all. It's all for HypoDD. And do you guys have questions about this?
Yeah, Yixin, I have a question about that travel time residual. Could you please go to that travel time data that you had just shown us?
Oh, yeah, sure. The dt.ct file, right?
Yeah, that is just showing us. Not this one.
The output, I guess.
Yeah, the output one, yes.
.reloc. Yeah.
Yeah, here you said that this negative -9 is the new travel time residual, and 153, 111 are the travel time residual from the old catalog, right?
No, like 153 is the time residual. And the -9 only means you didn't use cross-correlation data.
Okay.
Yeah, so these two are both time residual results, but this column is for catalog data, and this column for cross-correlation.
Okay, thank you.
Yixin,
Yeah.
those time residuals starting at 153. What's the unit of those residuals, please?
Yeah, it's millisecond.
Okay, good. Thank you.
Yeah, thank you. Mm-hmm.
Hi, Yixin. So this code only works for one-dimensional velocity models?
Yeah, right.
It cannot work for like three-dimensional models.
Yeah, it only uses one D.
Okay. Okay.
But I think you can try, like, I don't know, maybe because the 3D tomography model would be like different part to part, so it would be consistent in one area, right? And in that area, it would be 1D velocity model. So yeah, I guess that, but I didn't use that.
Yeah, okay, thank you.
Yixin?
Yeah.
Thanks for the talk. I have a question about the weighting function that you had in the inversion matrix.
Okay.
So I have two questions about, okay, you want to go to the slide?
Yeah.
Okay. You don't have to, I can ask without you going there, or you can go there.
Okay, yeah.
Yeah, thank you. It's about the weighting function. No, the first question is, I'm wondering, what does the weighting function do to the matrix, and how do you build those weighting functions?
Oh, okay. So let me see. So you have so first the weights you can set is for each iteration. Like during each iteration, it will consider your weights to weight the catalog data more, or the cross correlation data more, or p phase wave more or S wave. So you can set weights for those things. And also the program can also generate a set of weights for itself. Yeah. So it will like let me think how to say that. So each iteration it will get a time residual.
Okay.
And the program will consider the time residual to set different weights to each perturbation. So yeah.
I see.
Okay.
Thank you.
Yeah. Sorry for my camera. You guys cannot see me.
No problem.
I also get an external camera. Yeah, I didn't use my own camera because my camera has some problem, and I got another camera, but it didn't work either. So I don't know what to do.
No problem, Yixin.
It's
The
okay.
main thing is that we can hear you. Thank you.
Yeah.
Yeah.
Yes. Anyone else have problem? Sorry, have questions?
Yeah, one quick question, like how distance are those? What is the maximum distance and the minimum distance you used for event and distance, the station?
Oh, distance. So in the example, he used 8 for paired events and 120 for from events to station. And in my research, I think I used 8 and 200. Let me see where is it. Yeah, here. 8. Yeah. Oh, sorry. It's 10. This one. This one. This max sap is for hypocentral separation.
Yeah, and when using the cross correlation, so we take like two similar waveform to get a pair. So what would be like the good limit of the cross correlation values to assign?
Oh, for the cross correlation, Dr. Stephen Horton's code has its own threshold, like the threshold for just for cross correlation. So if these two, if the two events waveform are cross correlated well enough, and it will calculate the time difference. And that program doesn't consider the distance between events, only this catalog data, because the PH2DT input is only calculated for the catalog data, and the cross correlation data is already the time difference data. So
yeah, okay, thank you.
Yixin, can I ask another question?
Yeah.
So at what event station distance does this method break down? Can you use it to do teleseism, or it's only appropriate for regional and local events?
I think it's only appropriate for the local events.
You can't even use it for regional, right?
Yeah, I think it's only for regional.
Okay. Thank you.
Yeah, thank you. Okay.
And then, sorry, just quick question. Is there a distance limit? Maybe you can use it for events that are like greater than 100 kilometers from these measuring stations.
Yeah, I never tried that.
Okay.
But yeah, I think it's okay. Like, it's really far from the events, right? And as long as these two events are close to each other, I think it will work. Yeah, but I never tried. Sorry.
No problem, Yixin. Thank you.
Yeah. So, any more questions? So it is the end of today's talk. Thank you guys for coming.
Thank you,
Thanks,
Yixin.
Yixin.
Guys, can we give Yixin a hand?
Yeah.
Thank you.
For the presentation.
Thank you.
Yeah.
Yeah.
Yeah. Bye.
Thank you.
Bye, guys.
See
Yeah.
you.
Bye.
Yeah.